My name is Daniel, and my title is Levels and Distribution of Tetrodotoxin in the Blue Line Octopus in Japan, and with special reference to within body allocation. And first, what is Blue Line Octopus? Blue Line Octopus is a beautiful and small animal, but also very dangerous because it's highly venomous. And the venomous called tetrodotoxin, TTX, and it found it always found in Indo-Pacific shallow water in this big area. And TTX is a powerful neurotoxin, and it can block sodium channels in nerve cells, can cut the nerve sending signal to your muscle, and causes paralysis and stop breathing. And scientists guess that the toxin has two functions. It's offense and defense. And for the offense part, the octopus bites their prey and inject the toxin into their body to kill them. And the defense part, they store across the skin and muscle to make itself lethal to attacker. So if the fish eats octopus, the fish will die. And the purpose is we measure the TTX level in body to know amount, and we study distribution in organs to know which organs has most TTX level, and we understand the function to prove that the guess is true or false. So we already have the previous research from Australia, and Australian data shows high and consistent TTX level. This time we focus on Japanese octopus, and there are something we want to know is the regional and seasonal make their TTX different, or and how is TTX allocated within body? And the last one is the TTX is endogenous or exogenous. The endogenous hypothesis, that means the octopus can produce the toxin by itself. And this hypothesis also proposed in other pufferfish studies. And if this hypothesis is true, that means the octopus toxicity should be stable, because if every octopus produced by themselves, then there's no reason have big difference between them. And number two is exogenous hypothesis. It means they acquired from food resources. Scientists found that in octopus habitat there are some toxic crabs or snails, so maybe octopus will eat them and get TTX from their food. And if this is true, the sample will maybe have some difference because of location or season. And now is the sample. We collect 13 adult sample in 3 different areas in Japan. It's Kanto area, Kansai area, and Kyushu area. And we also found 3 newly hatched paralavi. And this means the baby octopus. And these sample, we collect them in different seasons, so we also can see the time, the difference. And we cut the octopus in 8 different parts of organs, like salivary glands, arm, skin, gonads, something like that. And we cut them to small pieces and dissolve it, break it to even much smaller, and centrifuge, and finally filter it to a clean liquid. And we put the liquid sample into this machine, and we can get the data of TTX. And the point is, we only use the number in the blue parts, because If it's too low in this gray part, the machine cannot give us accurate numbers, so we just treat it as 0. And this is our result. I choose sample number 9 because it has strongest toxic, and we can show that the silver gain have most concentration. That means this is the weapon used for attack, and the biggest amount is in the arm, in the muscle and skin, and it means this the defensive shield for the octopus to protect itself. And this picture is the concentration of salivary in different seasons, and we can easily see that the contour areas and in the spring, contour area show the lowest toxin, and the spring also show the lowest toxin. So this season and location make it different environment. And this is a concentration in the muscle and skin, and obviously we can see also the contour area and the spring is same, very low, so it's consistent with the salivary data. And we also found the 120 rule. The x-axis is the concentration in the muscle and skin, and the y-axis is the concentration in the salivary gland, and found a strong positive correlation between the salivary glands and skin. The concentration of salivary glands are always 20 times higher than skin. So this means this is a evolutional fixed rule. All the blue line octopus will follow this rule. Okay, and now we look at hypothesis. The evidence suggests the TTX is exogenous because we just know that the big difference between all the sample. And the difference because the environmental difference and affect their food, and their food different, so they get different amounts of toxic. And another they also find is the digestive gland, means their stomach are always very low or even undetectable. So it means the octopus, after they eat and consume, they transport the toxin to their glands or muscle or skin very fast. And this one is, they also found a female octopus, especially in winter, had a higher TTX level in their gonads compared to males. Male is very low. And also, 3 newly hatched baby octopus have TTX in their body. So it means females can transport their TTX to their eggs, and when a baby born, the baby can have TTX in their body, so it can protect them. Now it's conclusion. We found 4 main points. First one is toxins 2 different functions: the weapon and defense, weapons and shield. And next one is the 21 rule, suggesting an evolutionary fixed distribution pattern. And exogenous origin, regional and seasonal difference, and with very low digestive gland that suggest toxins are obtained from food. and transfer to their storage organs. And last one is maternal investment. The females transfer the toxin to their babies, and the baby can live more safety. Thank you.